I'm Lior Burko, and I will be talking about detecting the gravitational memory effect from equatorial Zoomwhirl orbits. This is work done in collaboration with Gaurav Khanna, and it appears on the archive for more information. The gravitational memory effect comes in two flavors. First, there is the regular or linear gravitational memory effect, and then there is the null, Christodoulou, or nonlinear gravitational memory effect, which is what I will be focusing on. These are gravitational waves which are sourced by the effective stress energy tensor of the original or parent gravitational waves. And for the extreme mass ratio inspiral problem, the memory effect is expected to be quadratic in the mass ratio. The reason being that the original or parent gravitational waves are linear in the mass ratio, and then when they act as a source term for additional gravitational waves, they pick up another factor of the mass ratio, so we end up with a quadratic dependence on the mass ratio. For that reason, the memory effect from extreme mass ratio in spiral is naturally thought of as being very weak and probably too weak to be detected. But as I will argue, there is a natural laboratory which enhances the memory effect from a specific extreme mass ratio in spiral system, and therefore they might be of observational interest. The memory effect is non-oscillatory, unlike the parent gravitational waves, and it is an hereditary effect. Specifically, it depends on the complete past history of the gravitational waves. It is also interesting from the theoretical point of view because it is related to certain symmetries in general relativity. The memory effect has some severe limitations for detection with terrestrial detectors. Specifically, the low frequencies of the memory effect, the restoring forces that return the proof masses to their pre-gravitational wave position, and a single event, even as strong as GW 150914, is not likely to be detected. However, the detection likelihood increases with the square root of the number of events in a certain population of mergers, and therefore when considering large enough populations, there are prospects for detecting the gravitational memory effect with terrestrial detectors. These limitations are not shared by free-falling gravitational wave detectors such as LISA. And indeed, it has been suggested that the signal from a coalescing supermassive black hole binary system, even a single one, can be detected with LISA. An interesting laboratory that enhances the signal for LISA could be Zoomwhirl orbits. Zoomwhirl orbits are typically high eccentricity, strong field orbits around rapidly rotating Kerr black holes. If you like, you could perhaps say that it is periastron precession on steroids. This is the orbital shape for a typical Zoomwhirl orbit. Let's start here from apoapsis. The companion is zooming in, executes a number of whirls, in this case 3 of them, very close to periapsis, and then it zooms back out to apoapsis. If you are looking at the gravitational waveform, in this case it's the Weyl scalar psi4, then we see a pulse when the system is in whirl phase near periapsis, then quiescence when the system is zooming out to apoapsis, and then zooming back in, and then another pulse when the system is whirling. And this pattern of pulse, quiescence, pulse, quiescence, pulse, quiescence, etc. repeats as long as the system executes Zoomwhirl orbits. So let's take such a waveform of pulse quiescence, etc. The memory effect is expecting to have a sharp rise when there is a lot of gravitational waves during the pulse, but when the system is quiescent, there will be hardly any change in the memory effect. So we expect the memory signal to be something like this. And in order to analyze it mathematically in an analytical way, we are going to model this by a sequence of mathematical distributional step function where the height of each step I'm going to denote by delta h, and the length of each step, that is the duration between two successive pulses, by t. So we are going to model the memory signal by sum over distributional theta functions. By doing a Fourier transform and summing over the number of steps, we can get the amplitude spectral density, and from which we can construct the power spectrum. In the low frequency approximation, and the low frequency approximation is the one we want here, because by introducing a very short rise time here, we are messing with a high frequency. So we expect our model to be accurate only in the low frequency approximation. So when we do the low frequency approximation and find the characteristic strain, we see a number of interesting features. First, the characteristic strain is independent of the frequency. Second, it is independent of the period. It is linear in the height of each step, and the most important thing for us here is that it is linear in the number of periapsis passages. So n here is the number of periapsis passages. It's the total number of steps that we have, total number of pulses that we have. And this linearity in the number of periapsis passages is what's giving us the enhancement in the characteristic strain. So we have tested this with numerical simulations which are not subject to any approximation. The analytical model that I was just presenting does not appear in the numerical simulations. These are full 2+1 dimensional numerical simulations. In the figure on the left, I'm plotting the memory signal in dimensionless units as a function of retarded time along future null infinity sky plus. And we see here the step structure, the staircase structure of the memory effect. Here we have calculated the memory effect for a number of spin parameters of the central black hole, and those are very fast spinning black holes. The fastest is 0.99999. And as we increase the spin parameter of the central black hole, the amplitude of the memory effect increases. We see here the shape of the orbit. As we change the spin parameter of the black hole, the periastron precession changes. We cannot see it here in the figure for the azimuthal angle phi as a function of time on this scale, but we can see it in the shape of the orbit because it is very sensitive to the spin parameter of the central black hole. This is the radial coordinate as a function of retarded time. Here the system is at apoapsis, zooming in to periapsis, and then zooming back out to apoapsis, and so on. We look at greater detail in the staircase shape of the memory signal in the figure on the right. On the lower panel, we are looking at the L equals 2, M equals 2 harmonic mode, and show both the plus and cross polarization state. We see that we don't have exactly a distributional step function structure, but it is not very different from it, and therefore we expect our results to not be very dissimilar from the mathematical model that assumed a distributional step function. The structure of the staircase, however, changes when we consider other harmonic modes. At the panel on the top, we see the L equals 2, M equals 0 azimuthal mode, and we see that there is more structure here. during the rise. And the reason is that during the whirls of azimuthal modes, there is no production of parent gravitational waves and therefore no contribution to the memory effect. So what we see here is just a rise when the system is close to approaching the whirl phase and when it's just exiting from the whirl phase. And then of course when it's zooming out and zooming back in, we don't see almost any contribution to the memory signal. Next we show the characteristic strain. On the left we see in bold blue the Lisa noise curve, and the magenta curve is the signal from the parent gravitational wave, here for a system at a distance of 100 megaparsec, when the central black hole is 10 to the 7 solar masses. The mass ratio is 10 to the -5, so the companion is a 100 solar mass black hole. And we see here the memory signal for a number of values of n, or different values for the number of periapsis passages. And we see here that the linear dependence on n on a logarithmic scale is pretty much satisfied in the actual results. And more importantly, if we have only a single periapsis passage, the signal for the memory effect is about 3 orders of magnitude below the Lisa sensitivity curve, and therefore the chances of detection are not very high. But if we wait for 1,000 periapsis passages, the signal increases, is enhanced, and falls within the good sensitivity band of Lisa, and therefore perhaps in principle be detectable. On the right we see the orphan memory effect. So we are changing the mass of the central black hole to 10 to the 5 solar masses. We take the mass of the companion to be 1 solar mass, such that we keep the mass ratio at 10 to the -5. And we see that the signal of the parent gravitational wave shifts out of the good sensitivity band of Lisa. However, the memory signal, because it is independent of the frequency, for n equals 1,000 periapsis passages, remains within the good sensitivity band of Lisa, and therefore can be detected as an orphan memory without detection of the parent gravitational wave. We also looked at different slices for the different harmonic modes. So we look here, you can look later at how the relative strength of different harmonic modes behave. Another thing that we looked at is the dependence on the semilatus rectum. So when we decrease the semilatus rectum, even by a little bit, by 1 part in 10 to the 7 in this case, the memory signal changes appreciably in magnitude. So here we go from magenta is large, blue is medium, red is small periapsis passage, and we see that correspondingly the memory signal increases, even though the rate of change of the memory signal is independent of the semilatus rectum. To conclude, what we are working on now is extending this work to non-equatorial orbits around very fast spinning Kerr black holes, and also examining the effects of orbital evolution under radiation reaction. So far we have only looked at geodesic orbit, and we expect some interesting effects in the shape of the memory signal to occur when we allow for radiation reaction. Thank you very much, and I'm hoping for some questions for the appropriate discussion session.